Hi everyone, in this video we're going to be learning how to calculate the probability of A or B. In other words, we're going to be learning how to calculate the probability of one event or another one occurring. And for that we're going to be learning about several things. First of all, the most important formula we'll be learning about is the disjunction rule, which will always allow us to calculate the probability of A or B. And I'll illustrate how to use it as well as how to derive it with this first example. Secondly, we're going to be learning about mutually exclusive events, also known as disjoint events. And we'll be seeing that when we're dealing with mutually exclusive events, the disjunction rule will turn into what I'll call the addition rule. Now, if you want to skip ahead to one section or another, I've cut this video into sections so you can skip ahead or go back using this video's timeline. All that being said, let's get started. The fundamental rule or formula that we'll need for calculating the probability of event A or B occurring is known as the disjunction rule. And it states that given two events A and B, the probability of A or B occurring is equal to the probability of A plus the probability of B minus the probability of A and B. And a more formal way of writing that, and it's a notation I'll use, is to state that the probability of A union B equals to the probability of A plus the probability of B minus the probability of A intersection B. There we go. Now I'll just go ahead and box these. That's the disjunction rule, and you need to think of this rule as soon as you have to calculate the probability of one event or another occurring. Disjunction rule. Let me quickly say that the two formula that I've boxed here are saying the same thing. The second one that I've boxed in yellow here is simply a more formal or mathematically correct way of writing it. But if you want to use the one that I've boxed in orange, by all means do so. Now, on the left-hand side of the screen, I've written an example that we're going to work through in just a minute. Before doing so, though, let me insist on something quite important. In probability theory, when we speak of the probability of A or B occurring, the OR is an inclusive OR. And what that means is, when we say A or B occurs, it means that either the event A occurs, or the event B occurs, or they both occur at the same time. And in fact, as we'll be seeing when I explain this disjunction rule, the fact that the A or B also includes the case where A and B occur simultaneously is exactly why we subtract this probability of A and B. But don't worry, we'll get to that. Let's solve this example. In a school's grade 9 class, we're told that the probability that a student studies French is 0.3, studies Spanish is 0.5, and studies both French and Spanish is 0.2. We're then asked to find the probability that a student taken at random studies French or Spanish. Well, let me quickly write SOL here, as in solution. The key thing to pick up on here is that we're being asked to calculate the probability that the student studies French or Spanish. The word OR here is what triggers us to use the disjunction rule. And so if I go ahead and say that the probability the student studies French is probability of the event capital F equals to 0.3, and if I say that the probability that a student studies Spanish, so capital S, is 0.5, then the probability that a student studies both would be the probability of F and S, or F intersection S, and that's equal to 0.2. Now, using these three probabilities as well as the disjunction rule, we can go ahead and state that the probability that a student studies French or Spanish is equal to the probability of French plus the probability of Spanish minus the probability of French and Spanish. Now, replacing each of these three probabilities by the values we've just listed here, this becomes 0.3 plus 0.5 minus 0.2. And so finally, we can state that the probability that a student studies French or Spanish is equal to 0.3 plus 0.5, which is 0.8, minus 0.2, so that's 0.6. And that's the answer. And what this example shows us is that provided we have the three probabilities for the formula, calculating the probability of A or B is quite simple. But why does this formula work? Well, to answer that question, let me use this example and push it a little further. Let's say for a second that this school's grade 9 class had 10 students. And I'll just write that at the top here. I'll say 10 students. I'm choosing 10 because that's quite an easy number to work with. Now, if there were 10 students in total and the probability that one of them studies French is 0.3, well, that would mean that 3 students study French. In a similar way, for the probability that a student studies Spanish to be 0.5, that would mean that 5 students study Spanish. And finally, for the probability that a student studies both French and Spanish to be 0.2, well, that would mean that 2 students study both. Okay, now a nice way to see how or why this disjunction rule works is with a Venn diagram. And so I'm going to make one for this class of 10 students. So if I do that here, I'll start by drawing a rectangle, like so. That's my universal set, which I call capital U. And inside this universal set, I'm going to draw the set which I'll call capital F, like so, inside of which all the students who study French will lie, and I'll name that capital F. And I'll also add a set capital S for the students who study Spanish. So that would look something like this. There we go. And now I'm going to represent each of the 10 students we have in the class by a little X mark. Here's what I mean. I know that there are 2 students who study both French and Spanish. And so I add 2 X marks right here. That's the overlap or the intersection of the 2 sets F and S. Notice that these 2 X marks are in both of the sets simultaneously. Moving on, I know there are 3 students in total who study French. Well, I already have these 2 students here, so I need to add another one right here. And this student only studies French and not both. In a similar way, there are 5 students who study Spanish. And since I already have 2 of those students here, I need to add 3 X marks in the set S. There we go. Finally, since there were 10 students in total, and at the moment we have 1, 2, 3, 4, 5, 6 on our Venn diagram, I need to add 4 students to the universal set. Say here, here, and here. These 4 students study neither French nor Spanish. Perhaps they study another language. That being said, our Venn diagram is now complete. Indeed, we've placed all of the 10 students inside it. Now, one way of calculating the probability of F or S occurring would be as follows. We could state that the probability of F or S is equal to the number of elements or students inside the union of F and S, so F union S, divided by the total number of elements or students inside our universal set. And when I speak of the number of elements inside the union of F and S, it means the total number of X marks we see here inside the 2 sets F and S combined. So that would be 1, 2, 3, 4, 5, 6. And so I can write that, that's equal to 6, over the number of elements inside the universal set, and that corresponds to the total number of possible outcomes. So in this case, the total number of students. And as we can see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is equal to 6 over 10, which equals to 0.6. And that confirms the answer we just found a minute ago. But although calculating the probability of F or S this way is perfectly valid, more often than not, we won't be in a position to either draw the Venn diagram or find how many elements are inside the union of F and S. And consequently, we'll need the disjunction rule. And here's how and why it works. Rather than finding the number of elements inside the union of F and S directly, consider this. We can state that the number of students inside F union S is equal to the number of students inside F, so N of F, plus the number of students that study Spanish, so N of S, minus the number of students who study both French and Spanish. And here's why we have to subtract the number of students studying both French and Spanish. The number of students studying French would be 1, 2, and 3. In fact, I'll write that underneath here. That would be 3. The number of students studying Spanish would be 1, 2, 3, 4, 5. And I'll write that as well. That would be 5. But as I was counting the X marks here, you may have noticed that these 2 were counted twice. Indeed, they were counted once for the number of students studying French, and they were counted again for the number of students studying Spanish. Since they've been counted twice, I need to take them away once. And that's why we subtract the number of students studying both French and Spanish. And as we know by now, there are 2 students studying both French and Spanish. Now, by all means check, but 3 plus 5 minus 2 is equal to 6, and that's the 6 we had on our numerator up here. Finally, to get from this result to the disjunction rule we have here, we divide throughout by the total number of students in the class, or rather the total number of elements inside the universal set. And so to be clear, I'm going to divide throughout by n of u, and so this becomes n of f union s over n of u equals to n of f over n of u plus n of s over n of u minus n of f intersection s over n of u. Each of the terms we have here is now a probability. On the left-hand side, we have the probability of f or s, and that's equal to the probability that a student studies French plus the probability that a student studies Spanish minus the probability that a student studies both. And that's our disjunction rule. And there we have it. That's how or why this disjunction rule works. And so as soon as you have to calculate the probability of one event or another occurring, you need to be thinking of the disjunction rule. Okay, as I said at the beginning of this video, we also need to know about a special case of the disjunction rule, which we'll use as soon as the events A and B are mutually exclusive. So let's quickly move on to the second and final slide, in which I'll tell you all about it. On the left-hand side of the screen here, I have a second example. On the right-hand side of the screen, I have an illustration that goes with it. And our objective here is to learn about the addition rule for mutually exclusive events. Now, another name for mutually exclusive events is disjoint events. Disjoint. There we go. And we say that events are mutually exclusive when they cannot both occur at the same time. So I'll just write that. That's cannot both occur, or cannot both happen. Happen, all right. Cannot both happen at the same time. The same time. And the simplest example of mutually exclusive events I can think of is when we flip a coin. Indeed, if I flip a coin, then it will either land on heads or tails, but it can't land on both. Consequently, the two events landing on heads and landing on tails are mutually exclusive. It's not possible on one coin flip for the coin to land on both heads and on tails. On a Venn diagram, the sets that represent mutually exclusive events don't intersect. In other words, if I had two events A and B, so if I have an event A here and another event B here, they don't overlap at all. And consequently, there are no elements inside the intersection of A and B. The probability of A and B occurring is therefore equal to 0. And this will always be true when dealing with mutually exclusive events. And so for mutually exclusive events, the disjunction rule simplifies quite a bit. And it turns into the addition rule for A or B. And it states that the probability of A or B occurring is equal to the probability of A plus the probability of B, which I'll also write as the probability of A union B equals to the probability of A plus the probability of B. And this is the addition rule for mutually exclusive events. Okay, now that we have the formula, let's go ahead and work through this second example. We're told that a box contains 8 paper slips, 1 orange, 2 yellow, 2 blue, and 3 green. A slip is taken at random from the box. Find the probability that the slip is blue or green. As always, I'll start by writing SOL as in solution, and now we can get started. The key thing to pick up on in this question is the fact that we need to find the probability of one event or another occurring. And so the word or needs to make us think of the disjunction rule as well as the addition rule. And to choose between the two, we need to ask ourselves whether or not the events picking a blue slip and picking a green slip are mutually exclusive or not. Well, for this example, which I've illustrated over here on the right-hand side, if we pick one of these paper slips at random, it will either be orange, yellow, blue, or green. But it's not possible to pick one paper slip and to get both blue and yellow, for instance, or blue and green. Consequently, the events picking a blue slip and picking a green slip are mutually exclusive. They cannot happen at the same time. And that tells us that the probability of picking a slip which is both blue and green is equal to 0. The disjunction rule therefore turns into the addition rule, which allows us to state that the probability of picking a blue or a green slip is equal to the probability of picking a blue slip plus the probability of picking a green slip. And since there are 2 blue slips, indeed we have 1 and 2 here, and 8 paper slips in total, we can state that this is equal to 2 over 8 plus the probability of picking a green slip. Well, there are 3 green slips, indeed we have 1, 2, and 3, so that's 3 over 8. And adding these two fractions together, we quickly find that the probability of picking a blue or a green slip is equal to 5 over 8. That's the probability of picking a blue or a green slip, which we could also write as a decimal as 0.625. And that's the answer. And there we go. We now know how to calculate the probability of one event or another occurring. Indeed, we saw the disjunction rule, which remember stated that the probability of A or B equals to the probability of A plus the probability of B minus the probability of A and B. And we've seen that if the events A and B are mutually exclusive or disjoint, then the probability of A and B equals to 0, which means that this term inside the formula disappears and the disjunction rule turns into the addition rule. And I'll even add that. There we go. And I'll say if the probability of A and B equals to 0, in other words, if they are mutually exclusive. And so now that we're finishing this tutorial, I hope you can see that all you really need to remember here is the disjunction rule, as well as the fact that for mutually exclusive events, the probability of A and B will always equal to 0. Indeed, remembering those two things will quickly allow you to rederive the addition rule whenever you need to, which is always better than cluttering your mind with all of the different formula. And there we have it. That's it for this tutorial.